Now, what I want is pretty straightforward. The record is spinning this way. I think there's some things about this problem that you probably need. But what I want you to do for me is real quick, what would be a free body diagram for the bug? Take a moment, put in your notes. I want to come around and see it. So, free body diagram for the bug. In the problem, the bug wants to stay on the record. So assume that it stays on the record. First, you guys do understand that this picture here is top down. This one's from the side. You understand that part, okay? I just want to make sure because once you understand that, this has to be a Newton's second law problem. In order for the insect to stay on the record, it has to be traveling in circular motion. We're told in the problem that the record's spinning at 33 RPM. We'll come to that in just a minute, just in case you don't know what that means, but it's spinning. The bug has to stay attached to the record or has to stay on the record based on what we're talking about here. So this has to be a centripetal motion problem. But our rules for our free body diagram don't change. Let's use this perspective from the side first. So I think things like, gravity will be easier to write down here. So is our bug experiencing gravity? All right, so downward arrow. Is our bug in contact with the surface? Okay, so upwards arrow has to be perpendicular to the surface. Now, what do you think holds the bug onto the record? It's got to be friction. If the bug doesn't experience friction, the bug travels in a straight line this way. In order for the bug to not travel in that straight line, there has to be a force applied to the bug that causes its path to curve. The only possible force that's left from the forces we have here is friction. Friction prevents one surface from sliding past another. If I want the bug to stick to that surface, there's going to have to be a frictional force towards the center of the circle. That would be a force in this picture this way. That's it. That's it. That's all there is. There were no new forces. And again, in order to travel in a circle, you must have an unbalanced force towards the center of curvature. Now, with that being it, you should be able to do the rest of the work, right? Should be able to tell me what the net force is in the x direction, net force in the y direction. I mean, this is just a standard Newton's law problem. Adding uniform circular motion doesn't change the problem as much as you might think. So net force in the x direction is going to be MAC. Net force in the y direction is 0. I see only one force in the x direction. That's friction. All right, that's going to equal MAC. There's two forces in the y direction, but they're balanced, so normal must equal the weight. Any questions? That's what Newton's laws can tell us. Now, we have more to add to this now. There are new things that we know. But once here, there are other things we talked about. First, centripetal acceleration. We can't calculate the acceleration the same way. The speed isn't changing. For centripetal acceleration, we have a relationship that tells us how big that acceleration has to be. That gives us a relationship now that's in terms of how fast the bug is going. I do want to take a moment and talk about that for just a minute. So let me get this distraction out of the way and say that we are spinning the record at 33 RPM. You've got to change that into something that tells you the velocity of the insect. How fast is the insect going in something like meters per second? This is known as an angular speed. Omega is a symbol we use for angular speeds. We're going to come back to that. I don't need you to know that now, but as an angular speed goes, the whole record is moving at 33 RPM. But the bug is traveling at a specific linear speed. I would hope that most of you would realize that if the bug were here, its linear speed would be different, right? Do you understand why that's probably true? You guys have been on spinny things before. If you don't understand why that's true, think it through. Both those positions allow a path that looks circular. So if the bug were on the outer one, it would do that path, right? If it were on the inner one, it would do that path. But they would both, if there are two bugs, they would both come back to this same point at the same time. Which bug traveled the bigger path? The one on the outside edge or the one in the middle? So the one on the outside edge is going faster, right? More meters per second. The question for me that I'm kind of trying to get from you is, do you know how to calculate how fast the bug is going in meters per second? If you don't, let's put some things here. A rotation is one circumference. The R part of RPM is a rotation per minute, a circumference per minute. It's traveling 33 circumferences every 60 seconds. That's got to be the linear speed of the bug. Do you understand why I did it this way? It does 33 circumferences every minute. I'll put in here that R here probably should be in meters in order to give you a velocity that's in meters per second. I think you have almost everything you need to now finish this problem, but I want to teach you something else, and that has to be the way to answer the question. The question asked, what is the minimum coefficient of static friction for the bug to stay on the record? That's the question. What we just did was analysis. We did an analysis of the problem that produced this and produced that. It doesn't answer the question. In order to answer the question, we're probably going to have to work in something that has to do with the coefficient of static friction. Now, I don't want to solve the problem for you, but what I do want to talk to you about is something that I call preserving the inequality. Many of you, when you see a problem like this, don't know what to do with an inequality. Some of you probably have some ideas, and I hope that you do. But for us, we want to end with an inequality. We want to end with something that tells us whether our value has to be bigger than something or smaller than something. So preserving the inequality is probably necessary for what we're going to do in here. If you've never had to do this before, a lot of students, all they ever learn is make this inequality and do substitution. I don't want you to do that. When you're asked about a minimum or a maximum, one of the things you should do is preserve this inequality. So here's how you do that. Instead of substituting away from this function, I want you to substitute into that function. This will preserve the inequality. For example, it is true that the frictional force has to be less than or equal to this. But we have an expression for the frictional force from here. We could substitute into the inequality. This leaves the inequality in place. So mv squared over r is less than or equal to mu s times the normal force. This is preserving the inequality. It leaves the inequality in place. In fact, I have an expression for the normal force. I could sub that in for the normal force. mv squared over r less than or equal to mu s mg. This is still just substitution, but I'm substituting into the inequality rather than substituting out of it. Now, I can actually solve this for the coefficient of static friction, which is what the question asked about. Cancel out the m's. That happens quite a bit in stuff like this. And I get that mu s has to be greater than or equal to v squared over gr. Now, the problem asked, what is the minimum coefficient of friction? This not only tells me the answer to that, but it ensures that it is a minimum. Right? It says that the coefficient of static friction has to be at least equal to v squared over gr. It can be greater, but it has to be at least equal to or greater. That tells you specifically that this is a minimum. All right? Preserving the inequality. I got another one I want you to do. And we're going to run out on time, so I got to make this quick. I want you to imagine this road that has a dip in it. Everybody see I got a road with a dip in it? Not a great looking road with a dip in it. Let's make a better road with a dip in it. That's better. Is that better? Not really. I've got some marks at the top that help me line things up. So there's my road with a dip in it. I have a car, has cruise control on, so its speed stays the same. It's going to go through the dip. There's going to be a time when it's at the very bottom of the dip. At that time, it has the same speed. It's going to maintain the same speed all the time. Could you draw a free body diagram for the car? Please. I can't spend a lot of time with this, but you're not mindful. And you need to be mindful. Sure, there are people who put friction here. If you put friction there, then you had to put some applied force here. This is not really what's happening, but I'll let it slide today. Because the car is not sliding. So friction probably behaves differently since the car's wheels are rolling. But it better be balanced because the speed of the car wasn't changing. Now, if you put a weight downwards, good, you should have. I would expect there to be weight downwards. But your normal force, well, it had better be larger than the weight. Do you understand why? The car's traveling in circular motion. Right? This is a circle. It has a radius of curvature based on something up here. But this is a circular path. If the forces were balanced, the car would travel in this straight line. Bad for the occupants of the car. In order for the car to travel in a circle, the normal force will have to be greater than the weight of the car to push the car upwards out of this ravine. This is why whenever you're on a roller coaster that has a dip, you feel heavier for that moment when you go around the dip. That's the car pushing upwards harder on you in order to get your direction of your velocity to change. Mindful of things going in a circle. This is going in a circle. I mean, you understand that the very next one I'm going to have to do is a dip this direction, right? You won't be fooled now, right? You're going to be right on the money for this one. You know exactly what to draw? Do it. So I'm going to ignore those sideways forces, all right? That's not the focus. I'll draw our weight downward, sure. Did you do the obvious thing then, make the normal force too small? I hope so, right? This is why you feel lighter at the top. It's not accidental. But, and pay close attention here, if we make the downwards direction positive, because that's the direction of the acceleration, correct? We want the acceleration to be downwards towards the center of the circle. This would be mg minus n equals mv squared over r. Right? Net force equals MAC. The weight of the car isn't changing while it's doing this, correct? The mass of the car not changing while we're doing this. The radius of curvature not changing while we're doing this. So you, driver of the car, can select the velocity of the car. If you start going faster, this side gets bigger. You follow that, right? What's the biggest this side can be? It's mg minus n. So the biggest that can be is when n equals 0, correct? Because there's no way the ground can pull down on the car. That's the limit. You go faster than that, there's not enough downward force to travel in a circle. So you become a projectile. this is how you would jump your car. You would go too fast. Gravity isn't enough to make you go in a circle, and so now the rules of projectile motion work. Don't do this, you'll jump your car. Now, roller coasters can get away with this because they can clamp onto the car and increase a downward force, right? Create a downwards normal force. So they can do this, but that means you in the roller coaster car are going to feel like you're being flung out of the car and against your restraints. And yes, there are roller coasters that attempt to do that. You'll notice whenever they do, they have pretty beefy restraints. But one thing I want you to realize, your car isn't clamped down. Again, another one of your homework questions. Got one more, and we will run out of time while discussing it, which is too bad. It's number 23 in your homework. And I'm a fan of these kinds of rides, or at least I used to be. Spinning you around in a circle is something that lots of rides attempt to do. Lots of rides. You ever ridden one of these where you're like on the inside against the wall and you feel like you're stuck against the wall? Lots of versions of this, mostly at state fairs, but Mission Space at Epcot, Teacups at any one of those rides or any spinny rides do this. In fact, some of the ones at the like state fairs will do one of those on you while you're riding. You ever seen that? Where you feel like you're stuck against the wall? What do you think the forces are on you while you're on this ride? Assuming it's spinning, and it has to be. Can you kind of realize what those forces have to be? The bell rings in 1 minute, so I can't spend a lot of time on it, and I don't want to, but weight's obvious, right? A lot of people screw this up, and have been all day, but you're touching the wall. That means there has to be a normal force this way. And that would suggest that the only thing keeping you from sinking down the wall is friction. All right. Try your homework out.